just to remind you, we took the DT beam results, and I went through how we designed the rebars based on the moment diagram. And then we showed how you show the steel and all that stuff. And then we went over this table. So today I want to do the same, but for the slab. Okay, for the slab design. So by the end of the day, you will be able to go to your project and design your slab and put it aside, and you're done. So you will see the time we're going to spend today, that's the design for all the slabs on the whole building. Just to kind of see the magnitude of that, and you'll see how simple it is. Speaking of the slab, last time we talked about, just as a reminder, this was our slab. Remember? And just let me go one step further back. When we started with our building, we said in order to make this one-way slab, we inserted this floor beam. We inserted one beam here. We called it floor beam or beam 2. We inserted another floor beam and another floor beam. So looking at the cross section, my spans for the slab is now 15, 15, 15, 15, and so forth, because I started with a 30 here and I broke it in half. So this is my slab then, 1, 2, 3, 4, 5, 6 spans. Remember that? So we took that, and we of course we determined the thickness of it from here, and then we went ahead and calculated the loads on it. That's not the right one, but it's the same one anyway. I'll show you. We calculated the loads. We ended up with a T equal 8, the thickness from the table, and then we ended up with the total dead load of 119. Okay, so we did all that. We talked about it many times, and then this was our slab where live load is 50, the dead load 119, and we calculated the load, so we ended up with W 0.25. So now we're gonna take this and put it in DT beam. Okay, so I'm gonna show you the one already made, so we don't have to waste the time. So you'll notice we have 1, 2, 3, 4, 5, 6 spans, and the load is 0.25. So you have to go to DT beam like this. Instead of 4 spans, you're gonna push insert a new span 5, insert a new span 6. The length of that is gonna be 15 in my example. Okay, so what about the area and the inertia? Okay, so let's go. So that's what we're gonna talk about next. So if I take the example I'm gonna use today, which is this one here, already sold, and I posted this on Beachboard, so you should have that. So from the table, I determined that the total thickness is going to be 7 inches for this example. Okay, 7 inches thickness for this example. And remember how we take 1 foot strip of the slab, 12 inches, so B equal 12 inches. Okay, and then I'm going to put the bars at the bottom. So D is going to be roughly 7 minus 1 inch equals 6 inches. And then the way we do it here, D equal H minus 1, 7 minus 1 equals 6. And remember, I don't know if you remember, the one is, we said that the clearance from the edge of the bar to the bottom is 3/4 of an inch, plus the radius of number 4, it's about 1 inch. So 7 minus 1 is 6 inches. All right, so we went through that in the when we did the example for the slab. So this is what the section I need. So if this is my section, what is the area? Area is 7 times 12, divided of course by 144 to give you the area in feet square. That's what you're gonna enter in the DT beam. How about the moment of inertia I? B H cube over 12. B is 12, H is 7, cube over 12, but of course make sure you convert the inches to feet, because the program is asking for I to be in feet to the power 4. Okay, so that's the area and the moment of inertia. Let's go back to that. So we said the length is 15, the area is 7 times 12 divided by 144. The inertia is bh cubed over 12 in feet to the power 4. Again, how do I know the units? Look at the bottom. Inertia, feet to the power 4. Area, feet to the power 2. Length in feet. Okay? And then the elasticity is what? That's the E, 57,000 square root of F prime C. But make sure it is in kips per inch square, not feet square, inches square. We talked about all that. And density is the 150 pound per cubic feet, but we want it in kips per cubic feet, so it's 0.150. All right, so you know all that stuff. And then you go to the next one and you start entering your loads, right? W1, W2, in this case is 0.25. 0.25, we went over that too. And you enter that for all 6 spans. Okay, and then you run your DT beam and you're gonna get the moment diagram. All right, just as a quick review for you. So once you get the moment diagram, it's gonna be very similar to what we did with the beams. There's a few things different in the slab, and that's why I wanted to do that today. All right, so let's start with that. So this is the moment diagram we're gonna get from when we run the DT beam I just explained. And then of course, remember the DT beam is gonna give us the maximum moments positive, which is the first 2, and the negative moment, the first 2 also. The others, the DT beam is not gonna give us on the graph, but you're gonna get it from the numerical values. And if you do that, I wrote them in red, or they're too small to read, but they are written right there. So for example, M sub U, the maximum positive here is 3.733 kips foot. This negative moment is 5.08, C minus 5.08. This one is 1.617. This one is 3.695, and so forth. So those are all the M sub U's that we have. Very similar to the beams, but notice the moments here are much smaller than the beam, right? Much smaller than the beams. Because the spans are small, and then the load is small, and then the thickness is small. And then look at this. Again, we're using mu over phi bd squared. We're not using the complicated ways they did those examples. Remember, they gave us like 4 or 5 methods to do design. We said the easiest way and the practical way is this one, when you do mu over phi bd squared. Mu over phi bd squared. So what I'm gonna do here different, I'm not gonna start with the first one. I'm gonna start with the maximum moment, and for a reason, you'll see why. So the maximum moment is this guy right here. It's always the first interior moment, the first interior support, which is this guy. Man, this is an exterior support. This is the first interior. The negative moment at that is gonna always be the maximum moment between the positives and the negatives. That's always gonna be the case. So what is my maximum moment is 5.08. And look, you can check. 5.8 is the largest number here. Of course, this is 5.08 due to symmetry. So I'm going to start with this one, and you will see why. When we did the beam, we started with this moment, and we went to the right. But I'm going to start with this maximum, you'll see why. So if I do that, I do mu over phi bd squared. Mu is 5.081. Remember, this is kips foot. I need to multiply by 12 to get it in inches and 1,000 to get it in pounds. Why? Because the table in the back, when you use this term, mu over phi bd squared, they want it to be in PSI. So I have to multiply the moment by 12,000. We've seen it a lot in the example. Divided by phi is 0.9, we assume it. B is what? Can anybody tell me what B is? What is B?
12.
12 inches, thank you. It's always 12 inches. When you're designing a slab, it's always 12 inches. If you're doing a beam, it's different from one beam to another, whatever it is. But in slab, we always take 1 foot segment and design that, and you can see the B right there. Thank you for that.
Oh,
D,
sorry.
yes.
That's what I was just gonna ask. Like, why is it that the cross sectional area was only 12 inches? So that's just standard?
Yeah, we remember we take 1 foot strip of the slab,
Ah, okay. Okay.
right?
I must have missed that. Okay, Professor, thank you.
No, let me explain it one more time.
Thank you.
You're welcome. So let's say this is the slab, okay? And then I have a beam here and a beam here. So the slab is sitting on 2 beams. So we said the way we're gonna design this slab is gonna deflect, of course, this way, right? It's gonna deflect that way.
Mm-hmm.
So we said the way we're gonna design this slab on all slabs. Let me change colors here. We take 1 foot strip. This is 1 foot all the time. And we design that. And then let's say we end up with 2 bars in this 1 foot strip. Then the next foot strip will have 2 bars. The next foot strip will have 2 bars. The next foot strip, 2 bars. So that's why we take 1 foot strip, and then therefore our, let me grab the pen again. I don't know why it drops it, but it's okay. So if you think about this, if I look at this strip here, so there's my beam. This is 12 inches. This is the thickness. Okay, this is the thickness, and this is the width, 12 inches, and that's what my beam is. So I'm designing a beam per se, 12 inches wide, 7 inches thick, and I'm gonna find the rebars in that beam. Once let's say I have 2 bars, guess what? I'll take another strip here, 1 foot, another strip here, 1 foot. But I don't have to do that. Once I do one, I will get the area of steel per foot. I go to the table in the back, and that's where I pick up the steel. It will give me number 4 at so many inches. All right? Is that clear?
Yes, Professor. The 7 inches in the height. How did you get that? If in your example, wasn't it 8?
Yeah, but I'm not using my example.
Oh,
this is a different example. Sorry.
Got it. Okay.
Yeah, thank you. Good catch. Yeah, I'm not doing my example. I'm just doing a different example.
Makes sense. Thank you.
Yeah, thank you. And just to kind of remind everybody, the question is, let me go to that. The question is, when I did my slab here, I ended up with, where is that? Let's see. Right here, no? Right here. When I did my example, I ended up with T equal 8 inches. But that's not what I'm solving. I'm solving a different slab. Sorry about that. So the example I'm doing here is different example, which is, and I took it from previous group from previous semesters to just show you that. And look how nice of a job they did, really. So you need to do good jobs like that. I added these by hand, of course. They didn't do that. I just used their sketch. So this is 7 inches because it's a different example. And even their slabs are not 15. I think this is 12.6 or something, 12.5, the slabs. The span, sorry. All right. So we got that. So mu over phi bd squared, we said we're going to multiply by 12,000. So once we get mu over phi bd squared for the maximum moment, it comes out 156.8. Once I have that, what are we going to do after that? Anybody? Once I have mu over phi bd squared, what am I going to do?
Go look for rho?
Exactly, thank you. We're going to go look for rho in the back of the book. And we make sure it is for F prime C 4,000 and Fy 60,000. We will find that rho equals 0.0027. Okay? This is where the important point is. But remember F prime C 4,000, Fy 60,000. If you look rho minimum, the minimum rho allowed is going to be 0.033. See that? So the rho we calculated is less than rho minimum. So what we gonna do? Anybody? Which row we gonna use? Anybody? If my row is less than the minimum row the ACI code tells me I have to do, which row am I gonna use? I'm gonna use row minimum because the code tells me row cannot be less than 0.0033. So I came up with 0.0027, then I must use the row minimum. Is that clear? See the importance of row minimum, we always check. So I must use the row minimum. Here it says, so use row equal row minimum equals 0.0033. All right? Does that make sense? Anybody, any question?
Professor, their row, their 0.0027.
Yes.
How did they obtain?
Are you looking in the book?
Yeah.
Okay, do you agree or no? Let me get my book. Let me get my book. Give me a minute. Sorry, actually, no. Let me open my digital book so we can all see it together here. 1 second, please. Let me switch screens. All right, give me a minute. We can do that.
Oh yeah, it is correct, Professor.
It is correct. Okay.
Yes.
All right, that's fine. So anybody have any questions? All right. So if you look up that row, it's going to be 0.0027 less than row minimum. Sometimes you're not going to even find a row value for your problem. It's not on the table. That means what? That means it's too small. So you will use row minimum. All right? So I think that makes perfect sense. All right. Once we get row minimum, we have that. Then we need to get the area of steel. What is AS equal? Rho BD, just like the beam. Rho is 0.0033, B is 12 inches, D is 6 inches. I can get my AS equal 0.24 inches square. Okay? 0.24 inches square. All right? Any question on that? Okay, let me go to the digital. I want to show you the slab table anyway. I know I did before, but it's good to do it again. Let me do that. Okay. So since we're here, since we're already here, let's show it. I'll change screen for a second. One more. Okay, so let me share screen again. So let's go back, if you don't mind. What was our mu over phi bd squared when we picked up rho? Do you mind? What was that value? 158, right?
Yes.
Anybody?
Yes, Professor. It fell
Well,
right in between. Yeah.
yeah, mu over phi bt squared was what, 158 point something?
Yeah, because it fell right in between 0.0026 and 0.0027, and they went with 0.0027.
Okay.
Yeah.
So that's where we picked it up. See that? But look where rho minimum is. Rho minimum is right here. See that? Look where rho minimum, 0.0033. So it's less than rho minimum, so we will use rho minimum. All right, that's first thing. Second, let's go to the table where we pick the steel for the slabs. I want to show it one time so so you can do that. So again, just as a reminder, rho minimum can also be obtained right here. F prime C 4,000, Fy 60,000. You can get rho minimum 0.0033 the same. Okay? And while we're here, somebody asked yesterday in the lab, well, how do I get rho maximum? Remember we said rho maximum? It's not here. Look, you see rho minimum, you see rho balance, but you don't see rho max. We said rho max is the value of rho in here corresponding to epsilon t equal 0.005. So the maximum rho is 0.0181. This was a question yesterday while we're here. Please, any questions, interrupt me. This is the table for the slabs. See, A6. Remember I said today we take one foot strip. We design that. If we end up with 2 bars in that 1 foot strip, then you will go another foot strip, put 2 bars, another foot strip, put 2 bars, another foot strip, put 2 bars. But that's not what we do. Once you find the area of steel, then you come to this table. Look at this. It says areas of bars in slabs, inches square per foot. See, inches square is the area of steel per foot, meaning for every foot of strip, for every foot or for every strip, that is 1 foot. That's what per foot means. So you don't have to do strip. Okay? So what was our area of steel? Anybody remember from the example? 0.24, is it? Should I switch back? Let me see. Let me switch back. See, our area of steel was 0.24. See that? That's what we calculated. Rho BD, 0.24. Okay? So let's look at the table for 0.24. So 0.24. And in slabs, 90% of the time, the main steel is number 4. Number 4, that's the steel we pick. So what is close to 0.24? Oh, I have 0.24. Look at that. It doesn't have that often, but you have the number. So you need number 4. See that? Bar number 4 at 10-inch spacing. Number 4 at 10-inch spacing will give you 0.24 inches. Is that clear? Anybody? Any question? See how easy it is? You just go to this table. Although we take 1 foot strip, so we can calculate the area of steel per foot. That's what this is here, inches square per foot. This foot is that foot strip that we took. So that's what it says. So if this is my area of steel is 0.24 in 1 foot strip, then my spacing has to be 10 inches on cents. See that? Very important table and very easy to use. Any question before I flip the...
Professor, I'm sorry, I'm trying to catch up a little bit. What do
Sure.
you mean? What do you mean by 10 spacing? Is it like along the slab, like on the cross sectional area?
No. What happened is you're gonna use number 4 bars, and let me draw that.
Yeah. Thank you.
You're welcome. So let's say, let me change the color here. So let's say this is our slab. And let's say this is our beam. One beam here and one beam here. So the cross section of my slab is gonna look like this. And then this is my support and this is my support. Okay, let me draw another line here. All right. So if I say number 4 at 10 inches, that means I'm gonna go ahead and put my bars this way. 1, 2, 3, and then so forth, such that the distance between the bars, this distance is 10 inch, that distance is 10 inch, that distance is 10 inch, that distance is 10 inch. Does that make sense? So that's what this means. This is the cross section. Let me draw another cross section. Sorry. If this is the slab, then I'm gonna switch colors. So my bar is gonna be at the bottom, that there, and this bar is this bar, but this looking at it from the side, this looking at it from the top. Mm-hmm. So you will take the number 4 bars and stack them along the span, and then the spacing between them is 10 inches on centers. Does that make sense?
Perfect sense, Professor. Thank you.
Okay, thank you. Any other questions, please? All right, so that's that. And we will see it on the graph now. So that's where the numbers come from. Let me switch screens again. We'll go to this. All right. So we come back to this 0.24 inches square. We said main steel. That's the main steel I just showed. It's gonna be number 4 at 10 inches on centers. I showed you how it's done in the table. So where do I place that? Here, the example I just illustrated was 1 span, but we have 6 spans. So remember, I took the negative moment here. And remember how I said the tension over the support is gonna be at the top, okay? And then the compression will be at the bottom. Okay, let's see. Why is this missing something here? I think the screen moved a little bit. Let me get another. Okay, here it is. All right, when I maximize, let me move this bar, maybe that's why. Okay, now you can see it. All right, so remember, I'm doing for this moment. The tension is gonna be at the top, so I need to put the bars over the support. So this support is gonna be here, this support there. Those are the negative steel. Now, I use the maximum moment and I get number 4 at 10 inches. So all these will be number 4 at 10 because all these moments are smaller than that. So look here, number 4 at 10 inches, typical negative steel. So all the negative moments over the supports will have number 4 at 10. All right? So really, this here goes right there also, and this is number 4 at 10 and number 4 and so forth. All right? Any question on that? Now, but this is very important comment here. If I choose the maximum moment and I ended up with rho less than rho minimum, guess what's going to happen with the rest of the moments? Because they're all smaller than the maximum moment, so I'm going to end up with rho minimum for all of them. Does that make sense? Because look, if you put moment here, look at that. Mu over phi BD squared, all of them is less than 156. This is 115, 49, 114, 64. So all of them is going to give you a row less than row minimum. So we're going to use row minimum. Okay. So if I use row minimum, then I'm going to have number 4 at 10 inches for all of them. So again, for the positive steel here, between this is going to be the positive steel, this is going to be the positive steel between the support. This is the positive. I show them different colors just so you can see them. But guess what? They all going to be the same number 4 at 10 inches on centers. Typical positive steel. Why? Because we're using the same row, which is row minimum. If row is the same, B is the same, and D is the same, so it's going to be the same number. If you don't believe me, go ahead and do these. Go do one at a time. Do MU over phi BD squared for this. Find row. You're going to find it less than row minimum. You're going to use row minimum. Row equal AS equal row BD. You're going to get the same number. So you're going to get the same number. Does that make sense? So that's how you're going to choose your steel, the positive between the supports at the bottom and the negative over the supports at the top of the support. Any questions? Okay. So look at this here. It says, look at this node. It says using the maximum moment, which is 5.08, which we did, yielded row equal row minimum. No need to check the other moments, which are smaller than 5.081, right? You can see it from here. Therefore, the same steel throughout the slab gonna be used. And that's why we're using 4 number 10 for here, 4 number 10 for them. Make sense? And most of the time in the slabs is gonna be like that. Sometimes it's different, but not a lot, but most of the time, is going to be like this because the dimensions are small. All right, what else in the slab we need to do? We also need something called temperature and shrinkage. Okay, so the temperature and shrinkage, its value is to take care of any movement in the concrete due to the expansion and contraction of the steel. So let me go back and draw this again. So let me draw my slab again. Remember we said that's the slab. So we said that the main steel is going to be in this direction. Okay. Now, so in the cross section is going to be right there at the bottom. In addition to this, we need to have steel for temperature and shrinkage, but that steel will be placed in the other direction, perpendicular to that. See that? That's the top view. In the section, it's going to look like a dot. Every bar will be a dot because you're looking at the end of it. Okay, that's temperature and shrinkage. We put it over the main steel. So that's what the temperature, and that's what I see those dots. See those dots? That is the typical temperature and shrinkage steel. We put them here, we put them there, we put them here, we put them there, and we all that. I change the colors so you can see the bars, but they're all the same. All right, any question on that? So how much steel do we put for that? The code told me, and we went over that. The code told me, let me put it here for a second, that the temperature and shrinkage steel is AS equals 0.0018 B times H, not B times D, B times H. 0.0018, B is 12, H is 7, 0.15 inches square. Okay, so 0.15 inches square. Usually, the main steel, as I mentioned, is number 4. The other steel perpendicular is number 3. Okay? So let's go together and pick up the 0.15. Let's go to the table. Okay. So 0.15. I'm gonna look at number 3, 0.15. Look at that, it's right there. So I need what? Can somebody tell me what kind of steel I need for this? Come on, how do I pick up the steel for 0.15? What bar number, first of all?
Number 3.
Number 3. Number 3 at, what's the spacing?
9.
9 inches, exactly. Thank you. So number 3 at 9 inches on center. See that? Number 3 at 9 inches on centers. Okay, that's where this comes from. So that's why here you see number 3 at 9 inches on centers. So, and that's where this bar goes. These are the perpendicular ones. And look at this, number 3 at 9 inches on centers, typical temperature and shrinkage steel. When I say typical, that means all of them are the same. You will see the word typical on construction plans in the field. They tell you typical, that means it's all the same like this. When I tell you typical, that means all these bars are the same, you know, and all that stuff. Instead of writing for every line like this, they just typical, so you know it's all of them. Okay, any question? So look at this. We just designed this slab. And this slab is gonna be used on the first floor, on the second floor, and on the third floor. No difference. So you're done with your slab design. Okay, this is what kind of steel you need and what the thickness you need. One more thing we need to talk about is this negative steel, how we're gonna make it float like this. Okay, then what we do in real life, we use what we call them chairs. We use steel chairs. Let me show them here. Let me do it in yellow. So we use chairs like this on both ends, and the bar sits on it, sits on top of it, okay? To make sure we leave enough room for cover at the top. And then we do them under all those. Maybe sometimes we do 3 chairs, however many you need. The other thing is, remember in beams, we fill these gaps. We said in the beam, let me go there. When we did the beam design, remember we determined the positive steel, the negative steel, positive steel, and we had these gaps here. Okay, we had these gaps. So we said we cannot leave those gaps because we want this to look like a cage. So we went ahead and filled the gaps with the minimum steel, AS minimum, using row minimum. So that came out to be 3 number 5, 3 number 5, 3 number 5. In slabs, we don't have to do that. We don't have to fill these gaps, okay? Because you know, you're talking about a beam, and beam is limited width, but the slab is the whole width. So we don't do that in the slabs. So when you draw it to scale, you're gonna see that you have a lot of room here. So you just leave it blank. It doesn't matter because the thickness is not that big, and then the chairs will hold that in place. All right. So that's what we do. Any questions on that? Any questions? So now with this, you should go back and please do that before next week, next class. Make sure you go and design your slabs. It's very easy. See, I gave you everything you need. You're going to have different numbers. Design them, put it in your 3-ring binder, and you're done. You don't have to go back like in the beams. We said you have to go back for the stirrups, shear reinforcement, because slabs do not have shear reinforcement. If you remember when we went, we'll see it in chapter 8. Certain structural members do not need shear reinforcement. One of them is the slabs. One of them is the footings. They don't need shear reinforcement. Okay? So if you do this, you're done. You're done with the slab, put it aside, and that's it. All right. Any questions, guys? Any questions? All right. So now let's go back to the project. So now what have we done? We did the beam designs. You should have be done with all that now, with the exception of the stirrups. We just did the slab design. Okay, and then next we're gonna go to column design. So what I'm gonna do after we finish chapter 5, which is next week, we will do that. We're not gonna need the whole class. Maybe half the class we finish chapter 5. The other half I'm gonna skip to chapter 9, and we'll come back to 6, 7, and 8. I'm gonna go to chapter 9 so I can show you how to design the columns. Very simple. We'll design the columns, and then the next lab we will design the column for your project. And then after that, then you're done, right? Because remember, the columns, according to this, we only have 4 columns that we have to design, 4 stacks. So you can do them after next week. And remember, we said 4 stack of columns like that. So we will do that next week, and you can design those and put them aside. You're done with the columns. So the only thing you're gonna come back to is the shear stirrups, which is not really a big deal for the beams. With that, then we're done designing the building for gravity loads. Okay, that means for gravity load, dead load, live load, our design is done. Oh, I'm sorry, with the exception of the footings. We have to design the footing later on after we get that. Then, of course, we live in seismic areas, earthquake areas. I'm gonna show you how to do the seismic design for the building, and we have to design the shear walls for this. So we're gonna put a shear wall in this direction, shear wall here, shear wall there, and shear wall there. So we will do those also. We have plenty of time, so we can do that. Okay, so that's where we're going with that. Now, as far as the midterm, I understand we have next week and then the week after before we take spring break, right? You guys agree with that? So we still have 2 classes before spring break. So, and I will, that's what somebody told me last night, but I will confirm that. If that's the case, we will have finished chapter 5 next week, and then the week after we'll do our midterm. This way you finish it before you go on spring break. Okay, and that will be from chapter 1 to chapter 5. And then when we come back from spring break, then we'll start the seismic design in the lab, and we will continue chapter 6, 7, and 8 and all that stuff in the class. All right, so that's where we're going. Any questions? Any questions from anybody?
For the midterm, Professor, how many problems do you usually put?
I usually put either 4 or 5.
Okay.
Most likely 5. This way, 20 points each.
Okay, thank you.
But they won't be that, will be exactly like we've been solving examples and what we've been doing in the class. So nothing tricky, but you need to know the material. Any questions from anybody? All right. If not, then we're done. Okay, we're done for today. So please keep up with me. Go and finish the slab. So, as you can tell, we're finishing early. So spend the rest of the time with your groups to talk about the design of your slab. Maybe go run the DT beam for the slab and all that. And then, you have plenty of times now. We're finishing those classes early. So take advantage of that, okay? And if you keep all this to the end, you're gonna be in trouble, trust me. Don't save everything to the last 2-3 weeks of the semester. You can finish them and put them aside. This way, all you have to worry about is the final. All right, any question?
Professor?
Yes.
So for assignment 2, the data for lab, for group 4 is missing.
Yeah, you told me that. Okay, thank you for reminding me. Let's check that. 1 second, please. So let me switch screens here. Okay. Yeah, thank you for reminding me. I told you to remind me, yeah. And then somebody remind me before we quit. I'm gonna take attendance, please. So 21. Okay, lab sections. So which assignment is it? I'm sorry. Assignment 2.
Yes, assignment 2.
Okay, assignment 2.
So all the groups, group 1, 2, and 3, they have their file, but for group 4, it's missing.
Okay. And let's see. So it says group 1, 2, and 3, but 4 is not there, huh?
Yes.
Okay. So what about did you get the value for F prime C and the data for the beam test?
Yes, we did.
So all you need then is to, let me click on that. I'll share screens with you in a second. So you're saying you don't have this, huh?
Exactly, yes.
Yeah, you have assignment number 2, group 1, group 2, group 3. So what you can do, my friend, is use the same as group number 1. Let me double check something here. 3. Yeah, go ahead and use number 1. So 1, 2, 3, and then number 4 will use number 1 again.
Okay, thank you.
All right, you're welcome. Any other questions? Any other questions?
Yeah, since we're in this lab already,
I'm sorry?
Yeah, since we're on this part of the
Yeah, no problem.
I'm confused on what to put on number 6.
Number 6?
Yeah, on this lab.
On this forms here?
Mm-hmm.
Okay. So number 3, number 4, number 5, number 6. This one?
Yes.
Okay. Let's see. For this beam, define the steel specification by filling the table. Okay. Okay, let's see. L1 for the previously designed beam, define the steel specification by filling. Bar size, quantity, bent bars, standard seismic hoops. Okay. You see this L1 and L2? Keep that in mind for a second. And we have straight bars. We don't have bent bars, so forget the bent bars. So we have straight bars and we have these seismic hoops. They are really, we don't call them hoop, we call them stirrups. So we need this one and the bottom one. So let's go and explain that. L1 and L2. There you go. So for the hoops, there was another graph here. Just bear with me. There was another sketch here, L1 and L2. Okay, here it is. So if you keep going down, right, there it is. For the hoops, there's L1 and there's L2. Okay, now our beam is 5 inches wide, right? So remember, this is gonna go inside of the box, and you need some concrete on this side and that side. So if this is 5 inches wide, let's say you want 1 inch from this side, 1 inch from that side. So 5 minus 2, so L1 is gonna be 3 inches. Does that make sense?
Yes.
Okay. For the L2, for the hoops, the beam is 6 inches deep. So again, we need 1 inch at the bottom, 1 inch at the top. So 6 minus 2 is 4. So L2 is 4 inches. That's for the hoops. Is that clear?
Yes, thank you.
Now we go to the straight bar. This is the straight bar. See, the straight bar, we usually bend them like this. And I'll show you the picture in a second. So this is how we bend them. This is gonna go into the beam that is 52 inches long. So if 52 inches long, we need 1 inch on this side, 1 inch on that side. So then L1 is gonna be what? Anybody?
50.
50, thank you. So L1 is gonna be 50 because 51, 52. And then L2 is gonna be what? Again, the beam is 6 inches deep. So what is L2 gonna be?
Would be 4.
4, thank you. 4 inches. That's it. That's what goes in that table. Does that make sense?
Yes.
Okay, very good. So right here, so then here you go, L1 and L2 in here. The bar size, it'll be like number 3, whatever bar size you use. The quantity, how many? 3 or whatever in your beam. And then here the standard seismic L1, L2. The bar size is gonna be pencil bar or whatever it is, 1/4 of an inch. And then the quantity, we already, I think, talked about that. It's gonna be, the spacing will be 2.5 inches on centers. They're gonna be about 20 of them, about 20 of that, because the spacing is gonna be 2.5 inches on centers. And that's it. Any other questions?
Yes, so this is actually not related to the content for now, but I sent you an email, I believe, 1 or 2 weeks ago.
Okay.
I will be gone next Friday.
Okay.
So I was wondering if I could, if there's like what link is it that you guys use for the Thursday? Because I remember you said
It's the same.
It's the same
Same link, yeah. It's the same. All the labs and the
lecture.
and the lecture is the same.
Okay, cool. And then the lecture on the lab on Thursday starts at 7. You said.
Yes, it starts at 7 o'clock after the that.
Right after the lecture. Okay.
I will make a note right now when I take attendance.
Okay. Yes. Yeah.
Okay.
I'm going to sit in on the lab on next Thursday, sir.
No problem. Any other questions before we take attendance? Any other questions? Okay, let's take attendance. Friday lab, okay. Alexis, I think Basilio, Basilio, not here, okay. Griffin Brown, make sure I'm in the right section. Friday, yeah, it's Friday lab.
Hi, yeah, I'm here.
You are Griffin Brown?
Yes.
Okay. Let's see. Joycelyn? You're here. I heard you. Joyce?
That's cute.
Joycelyn?
Yes, I'm here,
Angel?
Professor.
Yeah.
Yeah.
I recognize your voice.
Okay, thank you.
Okay. Arba?
Here.
Okay, thank you. Binyam?
Over there. You.
Binyam? Okay. Let's see. Adis?
Here.
Thank you. Gabriel?
Here.
Thank you. Raymond?
Here.
Thank you. Christian? Sean?
Here.
Thank you. Craig?
Here.
Thank you. Minwoo?
Here.
Thank you. Biri?
Here.
Prado? Thank you. Myra?
Here.
Thank you. Armando?
Here.
Thank you. Again, Alexis? Basilio?
I'm here.
You are? Okay.
Mhm.
And let me see. Binyam, are you there? Binyam is missing. Okay. So I'm sorry, who are you that you're going to be missing next week?
Sean Lowe.
Sean Lowe?
Yes.
Okay, I see that. Okay. All right, very good, no problem. Any questions from anybody?
Professor, I had a question real quick.
Yes.
For the test, how is it proctored? Like, do we just write it down and scan in to Dropbox, or is it on Beatport?
Yeah,
quickly?
what I'll do is usually I will email it to you or post it on. I will post it on Beachboard right on time, or maybe sometimes I'll give you a couple of minutes early, like 10 minutes early, 5 minutes early. It depends how I put the exam. If I feel that you need a little bit more time, I sometimes post it 15 minutes early or something. But I'll let you know.
Okay. Is it
And
conceptual?
I will put a deadline on the Dropbox, and
Okay.
you have to scan it and then drop it in the Dropbox. But you have to be very clear. And then I like to see full pages. I don't like to see 3x5 pictures and all that stuff. And then also I don't like more than one problem on the same page. So this way it's clear. Okay, we'll talk about that in the class when before the exam. But please start practicing that, because sometimes students write in very light pencil and it's so hard to see. So make sure you write clearly. Make sure you have a dark pencil or pen. Make sure you know how to scan and upload, and practice all that. And then what I tell people is that before the exam, prepare your sheets. Put all these sheets with your names on top. Problem number 1, problem number 2, problem number 3. Write all those before you start the exam, because I have some students who submitted with no names on it. No names. I have to go back to the post to see whose test is that. So get all that done so it doesn't cost you any time. Get everything ready. Put all your tools in front of you. Make sure however you're gonna scan it is ready, so you don't lose any time. And practice that. Practice to yourself and see how you're gonna do. So that's how it's done.
And then just one more thing. You mentioned 5 questions. Is it all going to be math-based, or are there any conceptual?
Well, what do you mean by conceptual?
Just like anything theory-related, like not any mathematical.
Everything is
No
theory-related.
derivations at all.
Okay.
No derivation. It's mainly solving problems. Sometimes I put one question, fill in the blanks, or true or false or something, but it'll be exactly from the discussions. So sometimes I put one problem like that, but it's very straightforward. Like I say, for f prime c equal 4,000, fy equals 60,000, row minimum equal blank. Okay. For f prime c equal 4,000, beta 1 equal blank. Okay, so things like that I do. But no derivation. You just use the equations.
Okay, thank you.
You're welcome. Any other questions? All right. So please, guys, use your time wisely. Go and design your slabs and finish with that. And then keep up with me, and we're discussing a lot of good stuff here. And then with that, if nothing else, have a good weekend and stay safe out there. Anybody else? Okay, thank you very much.